Welcome back. The topic of this lecture is Internet Protocol. The topics that we are going to cover are IP. First, we are going to focus on service model, fragmentation, and IP addresses. Then we are going to discuss subnetting and CIDR, and at the end, we will also discuss IP version 6. So by the end of this video, you would have at least some intuition about how do we interconnect different type of networks to build a large global network. And besides knowing about IP version 4 primarily and the topics of subnetting, CIDR, would also know how does IP version 6 differ from IP version 4. So far we have seen how we can use switches to build LANs and bigger LANs. In this video we are going to go beyond LANs and we are going to consider heterogeneous large networks. And for that we are going to use this term Internetwork. Internetwork is an arbitrary collection of networks. So these networks are not necessarily homogeneous networks. And furthermore, this collection of networks is interconnected to provide host-to-host packet delivery service. Here is a diagram of an internetwork. You can see there are 4 networks. There is one wireless network here. There is another network Ethernet here, network 2. And there is another Ethernet here, network 4. And then there is a point-to-point link connecting these 2 routers. That's another network. So these symbols represent routers, or they're also called gateways. And these are the devices that are used to interconnect different networks. And these devices with these letters H, H1, H2, and so on, they are hosts. We use this term internetwork with a small I when we are talking about a generic collection of networks. But when we are talking about the global internet to which we connect, we use this term internet with capital I. And this generic internetwork is also referred to as internet with a small I. What makes this internetworking of different networks possible is that all of these nodes, all of these routers, as well as all of these hosts run what is called Internet Protocol, or IP for short. This was designed and developed by Windsurf and Bob Kahn, and they were awarded Turing Award, which is the highest award in computer science, for their work on TCP and IP. As I said, IP runs on all the nodes in a collection of networks, and it's IP that defines the infrastructure that allows these nodes and networks to function as a single logical internetwork. IP also provides global addressing scheme, which allows us to identify every node and host in a network. We are going to come back to addressing in a while, but before that we're going to discuss some other aspects of IP. So let's go back to the diagram that we just saw. So suppose now these hosts H5 and H8 want to communicate, so they want to share files or something. So the connectivity between these hosts H5 and H8 is through this AP, through this router R1, then through router R2, and finally through router R3, going back to this network 4, finally to H8. And that is shown in this diagram. So here we have a protocol graph that is running on each host as well as these routers. And as you can see, this protocol IP runs on every host and every router. Right? There may be other protocols running on top of it, like here it's TCP, there may be UDP. And the the connection, let's say between H5 and this router R1 that we saw, that it's a wireless network, right? So the bottom of this protocol graph has 802.11, which is, as we know, it's Wi-Fi. However, this router connects on one hand a Wi-Fi network, on the other hand an Ethernet network. So it must implement both of these protocols, 802.11 as well as Ethernet. And so the connectivity of H5 to R1 is through Wi-Fi, right, which is 802.11, and between R1 and R2 here it's through Ethernet, right? So it's Ethernet, an Ethernet network, this network 2, connecting these two routers R1 and R2. And then between R2 and R3 there is a point-to-point link, right? So they are connected using yet another technology. And then finally R3 connects to the host H8 again through Ethernet, right? So in this case both of these are connected via these Ethernet links. And so as you can see, we have seen three different link layer technologies, right? We have Wi-Fi, we have Ethernet, as well as we have this point-to-point protocol. However, it's the IP, that's the glue layer that holds all of these together and allows this internetwork to operate as a logically, single network. This term IP service model refers to the type of host-to-host service that IP provides. And IP provides very little. It basically provides what you may call the lowest common denominator of all possible services that a network may provide. IP provides what is called connectionless or datagram model of packet delivery. So in this model, the entire information that is needed to take a packet from source to destination is present in the packet itself. There is no need to establish a connection before starting to transmit data. And actually, I mean that this design is influenced by this this principle to keep the routers simple. And IP provides what is called, again, best effort service. So IP tries its best to deliver the packet from source to destination, but it provides no guarantees. And that's why this is also called unreliable service. And so, IP just says that, I'll try my best to take your packet, from, source to destination. But in the process, packets can get lost. They could be delivered out of order. There may be duplicate copies of packet that can be delivered at the destination. And there is no guarantee how long it will take for a packet to reach its destination. The designers of IP made this choice of providing this minimal service deliberately because they were guided by the philosophy that internet should be able to connect any reasonable, let's say, networking technology. Now we are going to look at IP packet format. First, 4 bits indicate version. In the case of IPv4 it's 4, in case of IPv6 it's 6. Since this is the first field, it's very convenient place to have a version, because depending on the version we can change the interpretation of the rest of the packet. Then there is a 4-bit field of header length, and this indicates not number of bytes but number of 4 bytes, so 32-bit words. In the case of IP header, you see we have 1 2 3 4 5 32-bit words, and then there are some options. So if these options are not used, then this field would have 5. The next 8 bits indicate type of service. This is used to give, for example, priorities to different packets. Then there is a 16-bit field that indicates the number of bytes in this datagram, including the size of the header. And therefore, the maximum size of this datagram could be 2 to the power 16 minus 1 bytes, which is about 65,000 bytes. These next three fields, 4 bytes, are used in fragmentation. The first field, 16 bits, is it's an identifier, right, that identifies a particular datagram. So even if we fragment this datagram, this identifier remains the same. And then there are 3-bit flags, and then there is a 13-bit offset. So I will come back to this in a minute. Then there is 8-bit time to live field. Initially the intention was that we'll measure time, but the clocks of different routers are not synchronized. So basically when a router forwards a datagram, it simply decrements this by 1. So actually this is not strictly time, but this is number of hops. And then there is an 8-bit protocol field, right? So it's used for demultiplexing, and for example TCP is assigned number 6, UDP is 17. Then there is a 16-bit checksum field. Now we know how to calculate checksum. So this entire datagram is treated as a bunch of 16-bit integers, and then those are added using 1's complement, and then a complement of that result is put in this checksum field. Then we have these two fields, source IP address and destination IP address. And in the case of IP version 4, these addresses are 32 bits long. So we have these two 32-bit fields. Then the header may have some options, and if they are present, they are indicated in this header length field. And it's required that these fields at the end are aligned at this 32-bit boundary. One problem that comes up when we network heterogeneous different networks is that different networks have different maximum packet size that they can transmit. So one option is that if the packet size is larger than what that network can carry, basically that packet is dropped, but that's not a good idea. And then the second option is to send datagrams that are not larger than the maximum packet size that an intermediate network can carry, and that is possible. That's done. That's called path MTU discovery. And then there is a third option, which is a more general one, and that is to fragment a datagram, right, into multiple pieces if the datagram encounters a network that cannot carry the datagram in one piece. And so that is sort of formalized by this term called maximum transmission unit, and this term refers to the maximum size of an IP datagram that a network can carry. Note that once an IP datagram is sent to the link layer adds its own header and trailer, and therefore the actual frame size that is sent on a network so the maximum size that that can be sent over a network is actually larger than this MTU, because that also includes the link layer header and trailer. And here are two examples. So for Ethernet, MTU is 1500 bytes, and for fiber it's 4500 bytes. When sending a datagram, a host would typically not send a datagram that is larger than the MTU of directly connected network. And therefore fragmentation only happens when the datagram encounters a network along the way where the MTU is smaller than the size of the datagram. Now let us consider the this example that we saw earlier once again. So here suppose H1 sends a datagram to H8 of size 1420 bytes. So 1400 bytes data and 20 byte IP header. And so remember this was connected to router R1 using 802.11, so there is 802.11 header. Now router R1 was connected to R2 using Ethernet, and they happen to have the same MTU. So the only thing that changes here is the header is now Ethernet header. And now R2 and R3 were connected using some point-to-point link. And in this example, it's assumed that the MTU on this link is 512 plus 20 bytes, that's 532 bytes. Now, since the MTU of this link is less than 1420 bytes, this datagram is going to be fragmented on this link. So the first fragment is going to be 532 bytes, 20 byte header, and 512 bytes data. And then there is going to be another fragment because the total size except the header is 1400 bytes. So we have taken care of 512 bytes in the first fragment. The second fragment is also 512 bytes. And the third fragment would have 1400 minus 1024, that's 376 bytes. It's going to go in the last fragment. And these fragments are entire datagrams by themselves. As you can see, they have an IP header, and we'll come back to what goes in the fragmentation fields. But basically the point is from this router onwards, they would be carried to the destination independent of each other. And again, from router R3 to this destination, the MTU is larger than this one, but that does not mean that these fragments are going to be assembled at router 3. They basically are carried, as I said, independent of each other up to the destination, and it's the destination that will assemble these fragments. Now we are going to look at how the header changes as a result of fragmentation. So suppose this was the original header, right? So remember we talked about these three fields: identifier, then 3 bit flags, and offset, and we said that that's relevant to fragmentation. And so when the sender sends a datagram, it will put an identifier, right? And this bit is called more bit, and this is set to be 0. That means there is no more fragments. So this is a datagram that is all by itself. And then there is an offset field, and I will explain in a minute how this is used, but this is going to be set to 0 as well. And then there is rest of this IP header, and then this payload, and in our example the payload was 1400 bytes. Now in the first fragment, right, the identifier remains the same. However, now this flag is set. So what it means is that there are more fragments to this datagram, right? And the offset is still 0. will change in just the second one, and then rest of the header remains the same, and we have sent 512 bytes of data. Now the second fragment, the identifier is the same, and you should realize that this has to be the case for the destination to reassemble this datagram. And again, more bit is set because this is not the last fragment, right? So there's one more fragment coming up, and this offset is counted as 8 byte chunks of the data, right? So we sent 512 bytes here, and if you divide by 8, that gives us 64, right? And therefore the offset is 64. So in offset we count 8 byte chunks of the data that we have sent. And so now we come to the third fragment. So in third fragment, identifier is the same. Now there is no more fragment, right? So this more bit is now set to 0, and offset is 128 because we have sent so far 1024 bytes of data. Divide by 8, that gives you 128. Now you should be able to observe that by this design any fragment can be refragmented down the path, because suppose we want to fragment this further. So this fragment comes across a link where MTU is less than 512 bytes, and so that's not a problem, because in that case the let's say we have now two fragments, a fragment 1 and a fragment 2. Fragment 1 identifier is going to be the same, right? Now more bit, what does it tell? So in this case more bit is set to be 1, right? We are fragmenting in any case, so the more bit is going to be 1, and offset is going to be the same as before, 64. And let's suppose we refragment it equal size, so each one is 256 bytes. So the second fragment would have the same identifier as before. Now the more bit of the second fragment cannot be 0 because the more bit of this fragment itself is 1. That means on the destination there's going to be more fragments after this, so this is going to be 1. And as I said, so suppose we just cut into two pieces equal to 56 bytes and 256 bytes, and so the offset is going to be 32 plus 64, which is 96, right? Note that even if one of the fragments is lost, the reassembly will not succeed at the destination. And in any case, since the burden of reassembly is now at the receiver, it's better to avoid fragmentation, and one can do that by using what I referred to earlier. It's called path MTU discovery. And then send datagrams that are no larger than the MTU, the smallest MTU on the path. And there is another option also, that the sender can set no fragmentation bit, and in that case, if the datagram encounters a network where MTU is smaller than the datagram size, an ICMP error message is sent back to the sender. The Internet Assigned Number Authority, or INA, allocates IP address blocks to what are called regional internet registries, and these entities handle IP address allocation to different geographical areas. So AFRINIC is for Africa, Asia Pacific, means India, and Southeast Asia is handled by APNIC. This is US, Canada, so it's ARIN. In Latin America, it's LACNIC, and RIPE handles Europe and West Asia and Central Asia. And then these regional registries in turn allocate IP addresses to ISPs or to customers. Suppose this host A wants to send some data to host B, and they are connected over internet. In order for A to send data to B and not to some other host, it should be clear to you that the IP addresses that are assigned to hosts must be unique. IP addresses are structured, so actually they are hierarchical. Every IP address has two parts. There is a network address part, and then there is host address part. Network address identifies a particular network, and the host address identifies a particular host within that network. Since all in all we have 32 bits for an IP version 4 address, there are about 4 billion IP version 4 addresses. Initially, IP addresses were divided into 5 classes: class A, B, C, D, and E. Class A IP address has, that the address begins with bit 0, and then the next 7 bits are used to assign a network address. And then the rest 24 bits are used to assign host address. And among class A addresses, 0 is not used and 127 is reserved for loopback. So out of 128 possibilities, 126 class A addresses are possible. Then comes, so this was class A address. Now comes class B address. These addresses begin with bits 1 and 0, and then the next 14 bits are used to identify a network address. And so there can be about 16,000 class B networks. And then we have class C networks. These addresses begin with bits 110, and then we have 21 bits for network address. And that means that there can be 2 to the power 21, or about 2 million class C network addresses. As for the number of hosts that can be attached to a particular class of an IP address, in the case of class A, we have possibility of attaching up to 2 to the power 24 minus 2, which is about 16 million hosts. All zeros and all ones are reserved. In the case of class B, we have a possibility of attaching 2 to the power 16 minus 2 hosts, which is about 65,000. In the case of class C, it's 2 to the power 8 minus 2, that's 254 hosts. Then we have class D addresses. In the case of class D addresses, the first 3 bits are 1, and these addresses are reserved for multicast. And then there are class E addresses, which represent the rest, and these addresses are reserved for research and development. And thus about half of all possible IP version 4 addresses are class A addresses, quarter are class B addresses, and 1/8 are class C addresses. In this familiar way of writing IP version 4 addresses like 10.3.2.4, it's called decimal dot notation. What we are doing is we're basically separating the 4 bytes with a dot, and we are writing each byte as it's a decimal value. Now we are going to look at how datagrams are forwarded in IP. So recall that the destination address is present in the datagram. The second thing to note is that the network address uniquely identifies a particular network, and all the hosts in that network would have the same network address part, although they would have different host address part. If the node is not directly connected to the destination network, then it's going to forward to some router. Typically, routers have choices to which router to send to, and so each router maintains a forwarding table that has this form, network number, and next hop. So depending on the network number, it's going to send to an appropriate router, and that router hopefully is closer to the destination. And if none of these entries in the forwarding table match with the network address of the destination, then the datagram is forwarded to a default router, right? So every forwarding table normally has a default router where datagrams that don't match with any of the entries are sent to, and hosts typically would have just a default router. Now let us look at this example that we saw before. So here is the routing table for this router R2. So this router R2 is directly connected to network 2 and network 3. And so for these networks, it can just send directly to the interface through which it's connected to those networks. So for network 2, the table says send to interface 1. So this is the interface 1 of this router, and this is interface 0 of this router. However, if the destination address, the network number of corresponding to the destination address is 1, then it will send to router R1, because that's the way this datagram is going to go to this network. And if the network number corresponding to the destination address is 4, right, then it has to send to router R3, because router R3 is connected to that network, right? So this is how the forwarding table of a router typically looks like. So there is going to be also a default router, right? So if nothing matches, then send to that router. So now let's look at two examples with respect to this diagram. So suppose host H1 wants to send a datagram to H2. Since they are connected on the same network, H1 will send this datagram directly to H2. On the other hand, suppose H5 wants to send a datagram to H8. So in this case, H5's only choice is to send to R1, right? So it's likely its default router in its forwarding table. And then router R1 is going to forward it to R2, right? So in the forwarding table of R1, the entry would be network number 4, and then send to router R2. And then the datagram comes to R2. On R2, because it's going to network 4, H8 is in network 4, it's going to forward to router R3, and router R3 will see that it's directly connected to that network, so it's going to forward it to H8. So here is datagram forwarding algorithm. If the network number of destination is the same as network number of one of my interfaces, then deliver the packet to destination over that interface. So one example could be that let's say H9 sends a datagram to H3, and so once that datagram arrives at R2, right, the network number corresponding to H3 is 2, and it's going to see that it's connected to network 2 via interface 1, so its router R2 is just going to forward the datagram on interface 1. Otherwise, if the network number of destination is in my forwarding table, that means I'm not directly connected but I know the route, then deliver the packet to the next hop router, right? Again, you can just check. So in the case when H5 was sending datagram to H8, right, it was going through R2 and the destination network was 4. According to this table, the packet had to be sent to router R3, and so R2 forwarded to R3. And so that's this a step. Otherwise, deliver the packet to default router. Here is a forwarding algorithm for host. For a host, it's quite simple. If the network number of destination is my network number, means the destination is on the same network that the host is on, then simply deliver the packet to destination directly. Otherwise, deliver the packet to default router. Now we are going to look at subnetting and CIDR. Suppose there is a large company, or suppose there is a university, and university has, let's say, 5 schools, and he wants to set 5 networks for each school. And further, suppose each school requires 500 hosts that it has to connect. And so 500 computers you want to connect. Now from our discussion of IP addresses, so we had a class C address that allows 254 hosts, and a class B address that allows for 2 to the power 16 minus 2. It's about 65,000 hosts. And so for the 5 networks, right, school 1, school 2, school 3, 4 and 5, a class C address is not going to work, right? Because it allows for only 254 addresses, and we require like 500 and maybe 600 and another 500, maybe 800, maybe 900 IP addresses for each of these schools. And so the next is class B address. So we suppose we start allocating a class B address. So class B address to this one, let's call it some B1, then another class B address, and so on. But the problem is that there are only 16,000 or so class B addresses possible, because first 2 bits. So this is class B address. Remember, there are 16 bits for network number and 16 bits for host address, and out of these 16 bits, those first 2 bits are fixed. And so if we do this, then class B addresses would exhaust very quickly. So what we instead do is that we just take one class B address rather than allocating separate class B address to each one of these, because their requirement is not 65,000 hosts each, but it's like 500-600. And so we just allocate one class B address to this entire campus, and from that address pool, then every school is assigned few class C addresses, right? And that's accomplished using subnetting, right? So subnetting adds another hierarchy, right? So we already remember we had this hierarchy of a network number and a host number. Now we add another hierarchy where the host number is broken into subnet ID and host ID. So suppose this campus is assigned this class B address 130.55. Now using subnetting we can allocate several class C addresses to, let's say, different schools. So this might have an address 130.55.0 and 1. This could be 130.55.2 to 130.55.3 and so on. And so what subnetting does is it allows us to reuse a network number. So we allocate IP addresses within the network number to several physical networks, and these networks are called subnets, and they're short for subnetworks. From the outside, all of these subnets appear as just one network, right? A network with address 130.55, and therefore it requires just one entry in the routing table. However, for the routers that are inside this network, the subnets must be visible so that they can route packets appropriately, and therefore subnets are visible only from within the site. This sharing of single network number across different physical networks is accomplished using two things. One is called subnet mask and the other one is called subnet number. And subnet mask has this form of some ones. They may not be contiguous, but in this case they are, and followed by again some zeros. And this combined network number and subnet ID, this part of the address is called subnet number. And the combination of subnet mask and subnet number, let me just write this here, allow us to reuse the same network number across different physical networks. In this example we have started with a class B address, and then we have created these subnets where we have used class C address. And so what we have done is we have created this subnet ID, which is 8 bits, and host ID, that's another 8 bits. So what this subnet mask allows us to do is to do a bitwise AND on any IP address, and that allows us to determine the subnet number. So realize that since all of these bits are 1, and therefore whatever is the network number and subnet ID part of this IP address, it's going to give the subnet number, because anything ended with 1 is that thing by itself. And then since these bits are 0, anything ended with 0 is 0, and therefore all of these bits are going to come out to be 0. And so the result of a bitwise AND with a subnet mask gives the subnet number. And so all these hosts on the same subnet, right, would give the same subnet number when their IP addresses are ended with this subnet mask. We are going to consider this example. In this example there are 3 subnets, this one, there's another one here, and then this is the third one. And let's consider this host H1. So its IP address is 128.96.34.15, and on this subnet the subnet mask is 255.255.255.128. The bit pattern of this mask is first byte all ones, second byte all ones, third byte all ones, and in the fourth byte we have the first bit 1 and all the rest of the bits are 0. Now if we AND this mask with this IP address, then for the first byte we are going to get 128 back, because whatever the number is, if you bitwise AND with 1, you're going to get that number. Similarly, 96 and 34. Now 15 would have the first bit 0, right? So this is going to be 0. And so this is the subnet number corresponding to this IP address using the subnet mask, which is shown here. So all the hosts on this subnet will have exactly same subnet number. And let's quickly look at this second example, right? So we have this IP address 128.96.34.139, and the subnet mask is the same as before. Let's see what we get. So we AND with the first byte, get 128, then the second one 96, third 34. In this case, this number is larger than 128, so this bit is going to be 1, right? And so in this case, we are going to get 1 followed by 7 zeros, right, when we bitwise AND with 139. And so we are going to get 128, and that, no surprise, is the subnet number. Let's say there is another host connected to this subnet called H4. So the IP address of this host is suppose 128.96.34.55. And so if H1 wants to send some packet to H4, right, then it's going to figure out, right, so this is the destination address. It's going to figure out the subnet number corresponding to this IP address, and in this case, since they are on the same subnet, so it's going to give the same subnet number, and therefore the forwarding would take place directly. So H1 would directly send this datagram to H4. To make all of this work, now we have to extend our forwarding algorithm, right, to include this subnet number and the subnet mask. And this is how the forwarding table at R1 is going to look like. So it will have entries for subnet number and entries for subnet mask, and there would be a next hop. Right, so let's see how it works. So in the case of a datagram, right, let's say H3 is sending something to H4, right? So it will have this IP address 128.96.34.55. Now it's going to apply this subnet mask to this IP address, right? So this is what R1 is going to do. Once it does, it will find that this IP address corresponds to subnet number 128.96.34.0, and therefore it's going to forward that to interface 0. This presumably is its interface 0. This is its interface number 1. Now let's look at one more example. Suppose there is a datagram that arrives at R1 with the destination IP address of 128.96.33.14. And it's going to apply the first subnet mask to 55.255.255.128. It's going to give it subnet number 128.96.33.0 because it's 14, and that does not match, right? So the first entry is it's a subnet number where the third byte is 34, and this is going to give 33, right? So there's no match here. Similarly, you can verify there is not going to be match there. However, when it applies subnet mask to 55.255.255.0, it's going to get 128.96.33.0, and there is an entry for that. And what it says is that for this subnet number, it's going to forward it to router R2, which is the correct forwarding rule. And then once this datagram arrives at R2, it's going to be delivered to this host H3. And by the way, that's the subnet number that's shown here. So here is our IP forwarding that's modified to accommodate subnets. So let's suppose D is the destination IP address. And for each entry in the forwarding table, that we just saw has this form subnet number followed by subnet mask followed by next hop. We're going to do a bitwise AND of this destination address with this subnet mask. That would give us the subnet number. If the subnet number that we got is the same as the subnet number of that entry, then if the next hop is an interface, we just simply deliver this datagram to the destination. Otherwise, we deliver the datagram to a next hop, which would be a router. Otherwise, if none of these entries match, then we simply deliver to the default router.